Welcome to our review of chemistry. We're going to figure out what is going on chemically behind the various supplements that you take and everything that goes on with you and in your body so you can better understand the processes. My name is Rusty Owen Brink. I'm a board certified osteopathic family physician who's been working as an integrative physician for the past decade or more. This introduction to chemistry will start with the periodic table of the elements. It's a very impressive document. It's got a lot of information on it, most of which you will not need to understand what's going on. You'll need to understand. The first rule of thumb after memorizing the periodic table of the elements is to not panic. Don't let your eyes glaze over and don't run for your life. Seriously, you won't have to memorize this table. I do believe in the KISS philosophy. We will be keeping this quite simple. With that being said, the first element we'll consider is hydrogen. Hydrogen is the simplest of the elements. It is just simply one proton orbited by one electron. There are no neutrons. It's a very simple thing to look at it. The basics of an element. What is an atom? An atom consists of a positively charged nucleus composed of at least one proton and optionally neutrons. A proton carries a positive charge. Neutrons have no charge. They are electrically neutral. Negatively charged electrons, or in the case of hydrogen, just one electron, orbit around the nucleus of the atom. How big is an atom? That depends on the weight, the atomic weight of the element, which is the most pure form of an atom. Hydrogen doesn't weigh very much at all, as opposed to uranium or plutonium, which are quite heavier. Hydrogen has an atomic mass of 1, the weight of its one proton. A proton weighs about as much as 1,836 electrons. You can think of an electron as having just a point charge with essentially no mass at all. What is an atom? Size is an important concept to grasp. To put this into scale and perspective, picture the hydrogen proton as the size of a golf ball. The electron is orbiting in 3 dimensions like a spherical cloud, but it orbits very quickly, looking like a cloud that is 0.9 miles away from the proton. An atom is mostly empty space within this electron cloud. An ion is formed when the number of electrons is not equal to the number of protons in an element. If there are too many electrons, it will have a net negative charge. Too many protons or not enough electrons will give us a net positive charge. Most of the mass or weight of the atom is the nucleus. The proton plus the neutron makes up the nucleus. The volume of the atom is actually going to be the electron cloud. Helium will be the next element that we'll consider. It has a mass of 4 compared to that of hydrogen, which is 1. Why does it weigh so much more? It has 2 protons and 2 neutrons for a mass of 4. The number of protons determines the name of the element. Each element has a unique number of protons. Varying the number of neutrons creates what we call an isotope. Helium is on the far right side of the periodic table. It has 2 electrons in the S shell. It's what we call a Nobel gas. Wait a minute, what's this shell business all about? That's a good question. We'll start making this more interesting. Don't groan. Bonds. Chemical reactions happen when the electron clouds of different elements interact, causing them to bond together. A compound is a collection of different elements bonded together. These different elements are bonded together either by covalent bonds, which are interactions of 2 electron clouds, such as carbon dioxide, which has 1 carbon and 2 or dioxygens, or ionic bonds, in which differently charged ions are attracted to each other by electrical charges, such as sodium plus and chloride negative. This is table salt with the plus and the minus charges. Water has a different type of bond called hydrogen bond. That's hydrogen bond, not hydrogen bomb. Electrons typically orbit the nucleus in pairs. Each member of the pair spins in completely opposite directions. The S sublevel can only hold 2 electrons. It's a simple sphere in concept. The P shell can hold 6 or 3 pairs of electrons. The D sublevel can hold 10 electrons. The F sublevel can hold 14 electrons. The most stable and least reactive elements have an empty, full, or half-full electron cloud, which is also known as a valence. The half-full one is called half-full because of the electron spin. The electrons that there will all be considered to be spinning in the same direction, and they have not had their opposite twin join into the orbit that's spinning in the opposite direction. This is an example of what these various electron clouds or sublevels will look like. The s orbital, you can see, has got 2 electrons spinning around, and it's basically a spherical product. The p orbitals are more of a 3-dimensional 3-axis pattern. Then you get the 3-dimensional axis pattern, which actually is superimposed on the spherical s orbital. D orbitals will be a little bit different. That will be superimposed also. So to try to visualize these, your mind needs to understand geometry and be able to kind of visualize in your mind's eye what is going on here. That's one of the more complicated parts of this lecture. Electrons in the highest occupied energy level of an atom are called the valence electrons. These electrons determine the element's properties. The periodic table of the elements is organized according to this principle. This principle predicts what other elements a given element will be able to react most readily with. Valence electrons usually occupy the outermost shell. A radical or free radical is a molecule containing an unpaired free electron that readily reacts with most things. This can cause damage and react in an undesired way, an unplanned way with other compounds. An example of this would be something called a reactive oxygen species, which we'll get into later. Periodic table and valences. This is what the periodic table looks like. On the far left upper corner, we see hydrogen with an H. Progressing all the way to the right upper corner, we see helium with an HE. Hydrogen has 1 proton and 1 electron. Helium, as we reviewed, has 2 protons, 2 neutrons, and 2 electrons. Going back to hydrogen, going down the column, you'll see that it's hydrogen, lithium, sodium, potassium. Looking across the row, on the second row, you'll see lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Lithium will have 1 electron. Beryllium will have 2 electrons. Looking across, you'll see that boron has room for 3 bonds, carbon for 4, nitrogen for 3, oxygen for 2. Fluorine will have 1 ionic bond available, and then neon is what we call a noble gas. It will not bond to anything. We're not going to deal too far down the vertical columns. However, most of what we do will be across the upper portion of the periodic table of the elements. Group 18 consists of the noble gases. The noble gases have a full valence of electrons. They don't really want to react with anything. They're extremely chemically stable. Group 17 would be the halides. Their valence is open for just 1 bond. They have an unpaired electron just waiting to bond to something. Group 16, their valence is open to 2 bonds. This would be including oxygen. They've got 2 pairs of unbonded electrons, but they also have 2 matched electrons that will participate in hydrogen bonding as well. Group 14 contains carbon. This is the biggie. Silicon is also in this group. They like to exchange electrons and bond in 4 different directions. When a carbon atom typically bonds to something, each bond, try to figure this in a 3-dimensional image, will be about 120 degrees apart from the next bond. So in all 3 directions will be 120 degrees. You can think of it almost like a pyramid where there are 3 bonds available on the base and 1 that sits straight up, but they're all at 120 degrees apart. And this is an important concept that we'll come back to in the future. Silicone seems to have a physiologic role mainly in osteoporosis, but we're not really going to worry about this too much. Again, carbon is the biggie. Group 13 includes boron. The only atom in this group that we're going to look at is boron. Boron likes its electrons in threes. Aluminum really has no role in the body and is mild toxic. Like with group 15, moving away from group 14 in your direction, the valence will be three bonds that it would like to form. Group 12 includes zinc, which is a catalyst for certain enzymatic reactions. Cadmium below zinc is a toxic metal. Group 11, copper, which is also a catalyst. Silver, Ag, is toxic to microbes and thus is useful as an antibiotic as it does not harm humans too much, although it is possible to overdose on it. Gold, Au, is also in this group and has been used to treat rheumatoid arthritis. Group 10, nickel, is another catalyst. Palladium, Pd, has no known biologic benefit. Group 9 includes cobalt, which is the basis for vitamin B12. Rhodium, below cobalt, has no known biologic activity. Group 8 would be iron, which not only binds oxygen in the blood as part of the hemoglobin, but is also a key component of the cellular respiratory enzyme systems that allow the electron transport system to function, that generates and captures chemical energy. Rubidium has no known biologic benefit. Group 7 includes manganese, another enzyme that is a catalyst. It's a metal. Technetium has no known biological function. That's located below manganese on the table. Group 6, chromium, Cr, can be very necessary depending on its valence state. The 3+ valence state is necessary for health. It's important for diabetes control. However, the 6+ valence state is highly toxic. Molybdenum is necessary as a cofactor for enzymes responsible for removing sulfite and urate groups. Group 5, vanadium, designated by V, is involved in carbohydrate metabolism. Deficiency of vanadium can cause reduced growth and impaired reproduction. Niobium, Nb, has no known biologic function. In Group 4, titanium, Ti, has no known biological activity, but it is used in metal prosthetics for hip joints and also for other uses. The periods are known as the horizontal rows in the table. The lower down they are, the heavier and greater their mass, the greater the atomic number of protons, neutrons, and electrons. As far as the neutrons and protons are concerned, one thing I did not mention earlier, there's a term called isotope, and an isotope refers to a different number of neutrons in a given element. So it would have the same number of protons and electrons, but it may come in a couple of different formats where there's a different number of neutrons involved. This is in nuclear reactions. There's a greater potential for toxicity and poisonous activities the farther down you go on the periodic table. That's where the term heavy metals come from, and these heavy metals are indeed toxic and can poison many enzyme systems and cause death. The less reactive they are, the lower they are on the table as well. Equations. When figuring out a chemical reaction, both sides of the equation must balance. This is just like algebra, but a whole lot easier. For instance, 4 H2s, hydrogen wants to bind to another hydrogen, so we call it H2. That way there would be 2 electrons spinning around, and they could counterbalance each other in terms of the electron spin is concerned. They meet up with 2 oxygens, 2 of the O2 molecule, and just like hydrogen, the O2 wants to come up in a pair. So 4H2 plus 2 O2s will give you 4 molecules of water, 4 H2Os. If you'll notice, you've got 8 hydrogens on both sides of the equation, and you've also got 4 oxygens on both sides of the equation. So this is a balanced equation. Hydrogen has a valence of 1 in the S shell, so it wants to partner with another hydrogen. So as we discussed, that's what the usual state of this is. It's a gas. And the oxygen has the 2 electrons in its P shell that want partners. So again, 2 oxygens will link up as a preferred state. It is possible for 3 oxygens to link together. That's called ozone. It's not real happy in that state, and it's a very highly reactive radical that tends to get in the way and cause problems and damages to structures, etc. This is one of those reactive oxygen species that we've talked about earlier. It takes four hydrogens, four H2s and two O2s to make the four H2Os, giving us that balance. Next type of equation that we're going to talk about, or reaction, is called a redox, or reduction and oxidation reaction. These are chemical reactions that involve the flow of electrons from one molecule to another. All chemical reactions can be written as equations that must balance, and these are no exceptions. In a reduction reaction, an oxidant will lose an electron that will go to the product. In an oxidation reaction, the reductant will release the electron to a product. The oxidation state of these two involved reactants change in this type of reaction. Oxidation describes the loss of electrons and the acquisition of a negative charge. It's an increase in the oxidation state. Conversely, reduction is essentially anti-oxidation. This is the gain of electrons and a negative charge. This is a decrease in the oxidation state. So in all these reactions, there will be one donor and one recipient. And when the electrons move, they're actually transferring energy. You can think of energy as in a form of chemical energy, just like you put gasoline in your car to go down the road. The gasoline is oxidized by oxygen in the air, and when it does that, it releases energy in the form of heat, which is what causes the gasoline to explode and drive you down the road. Life happens also by taking advantage of this energy flow, just like your car does, but a little bit more complicated. These reactions occur, and your body has enzyme systems that capture this chemical energy, then use that captured energy to create other chemicals, then drive the reactions that are needed for life. The electrons are literally a form of energy. They're just stored energy that takes place in reactions and gives us energy for life. In biological systems, a proton will follow these electrons as they migrate from one molecule to another. NAD will gain an electron and become NADH, and then at a different point along the sequence, the NADH will lose the electron and the proton will follow. So this is a reaction that uses energy to move an electron onto the nicotinamide adenine dinucleotide, which will then donate that electron later on down the road to create another thing called ATP that will generate and carry energy to where it's needed in the cell. And again, the proton, the H, follows the electron, making it actually look like the movement is a hydrogen. The electron is going first, and the proton is sort of along for the ride. There are no neutrons involved in this, which makes it a whole lot easier from a thermodynamic and energetic perspective. NAD is reduced to NADH. For this to happen, the electron hydrogen donor was oxidized. Reduction and oxidation, you must remember, this happens together. There's an electron donor and an electron taker. There cannot be a redox reaction without a donor and recipient. Again, I just want to really stress this point. The process, again, represents the flow of energy. This is a very important concept as well. The more energetic molecule is giving up some of its energy in the form of electrons with a hydrogen tagging along. This makes it a less energetic compound. In the place where the electron went, we become more energetic. This transfer of energy, again, is what drives the chemical reactions that constitute life. These reactions are harnessed and guided along by enzymes in most cases. Glucose is a carbohydrate, which is abbreviated CHO for future reference. It has a chemical composition of C6H12O6. Carbohydrates and protein provide 4 calories of energy per gram. Fats are essentially hydrocarbon chains with a basic structure of CnH2n plus H2. This is a simplified version. There may be phosphorus groups involved. There may be oxygen groups involved. But that's the basic structure of what a carbon and hydrogen chain look like. Fat provides 9 calories per gram. Fats have little oxygen, so they weigh a lot less than carbohydrates. That makes it an ideal storage form for energy. So for those of us who have a little bit too much around our middle, we're carrying around a lot of extra energy that doesn't weigh as much as it could, but certainly more than we would like. In terms of energy production then, C6H12O6 combines with 6 oxygens to make 6 carbon dioxides and 6 waters for the 4 calories per gram that we talked about earlier. The hydrogen ion and pH will be the next topic that we will discuss. Let's conquer that proton. This is the basis of pH, the amount of reactive protons available on a log base 10 scale. I'm not going to worry you too much about the mathematics though, so relax. The pH has to do with the concentration of free protons available. The lower the number of the pH, the more free protons are available. These are highly reactive. And the lower the number is, the more of them that are reactive and the more damage that can be done. Everybody knows that a strong acid does a whole lot more damage than a weak acid does. A high pH, conversely, means there's an alkaline environment. Alkali like to receive those protons. So for any reaction between an acid and a base, one will act as a proton donor, the other as a proton recipient. This is kind of similar to the redox reactions. Now we're dealing with electron flow that carries energy along. Now we're strictly dealing with proton flow. And again, the proton is nice because there's no neutrons involved, so it's a pretty simple, easy reaction to keep track of. Also, if you have a strong acid, a weak alkali will be able to take that proton. Conversely, a strong alkali could take the proton. A strong alkali can receive the proton off of a weak acid. Whenever a proton changes positions like that, and if the acid and the base bind, okay, alkali is also referred to as a base, now we're talking about a salt. Just like sodium chloride is a salt of sodium chloride, you can have acetic acid, which is vinegar, and sodium hydroxide get together, and then you would have sodium acetate plus an H2O bond that comes with H2O that would be produced as well. The Henderson-Hasselbalch equation shows the relationship of pH in the solution and the pKa and pKb, which is the dissociation concept for the acid and for the base, respectively. This is essentially the concentration of acid and alkali. pKa refers to what's called the dissociation constant, or how tightly bound the proton to the parent molecule. pKb refers to how tightly bound the base alkali is to the parent molecule. For our purposes, we're not going to delve any more deeply into the specifics of these concepts. I do want you to understand that when an acid and a base get together, they form a salt plus water. The most important takeaway from this also is that the normal pH of the body is 7.40, and the range of normal is actually from 7.35 to 7.45. That is the range in which our enzyme systems work the best. Osmolality. Osmolality simply refers to the amount of dissolved material in a solution. Adding salt to a glass of water increases its osmolality. Enzymes are highly affected by osmolality. Proteins require the appropriate osmolality to properly fold into the configurations needed to do their jobs. The dissolved material can include salts, proteins, sugars, carbohydrates, whatever cellular constituents such as nucleic acids, etc. are available. All of these things increase osmolality. There is a normal range of osmolality in human beings, just as there is a normal range for pH. There is a normal osmolality for the intracellular space and for the extracellular space. The next topic we'll explore is called hydrogen bonding. If you look at the diagram in the right lower corner, you'll see that there's a red oxygen with 2 covalently bound hydrogens in gray attached. Water is a fascinating compound. It's known as the universal solvent. Water consists of the red oxygen and the gray hydrogens, as noted, but that oxygen has two pair of unreactive electrons. They're not really bonding to the oxygen, but they are still attached to the oxygen, And although not ready to bond, they still have an ionic influence on any nearby hydrogens. So they attract those charged protons to the hydrogens, and they will actually form a bit of a lattice or almost crystalline structure, as you can see in the diagram. So remember, the oxygen is bound covalently to the hydrogen, but those hydrogens are going to be attracting, the oxygen will attract nearby hydrogens by way of this ionic interaction, and this is called a hydrogen bond. Now we're going to start delving into some organic chemistry. This is considered to be the bane of pre-medical students everywhere, but it turns out to be fairly easy to use if you've got the right mindset. Algebra is to general chemistry what geometry is to organic chemistry. So if you did better in geometry in school, you'll probably find that this is very easy to deal with. This is a good rule of thumb from my personal experience. There are several geometric shapes and structures that need to be understood with organic chemistry. Understanding the prior concept of general chemistry is essential, however, to really understand what's going on with organic chemistry. Organic chemistry is the chemistry of carbon, C, oxygen, O, hydrogen, phosphorus, P, sodium, Na, chloride, Cl, and some metals thrown in for seasoning in good measure. We'll be dealing primarily with covalent bonds in the organic chemistry. From the valences and groups of the periodic table, recall that carbon has 4 available binding sites. Nitrogen, boron, and phosphorus generally have 3. Oxygen has 2 bonding sites for covalent bonds, and also 2 pair of electrons that are out there that will attract hydrogen bonds and allow for hydrogen bond formation. Group 1 includes the hydrogen, sodium, and potassium. Each of these have 1 available bond. They're also the most likely to have the ionic bonding. As alkaline metals, they accept protons well, better than group 2, such as calcium and magnesium. Group 2 are known as the rare earth metals. Magnesium and calcium each have 2 available bonds, and they can also ionize and go to the Mg++ or the Ca++ form for their ionic bonding. Beryllium really does not participate very much in biology, so we're not going to worry about that. Metals also bind into these organic chains. Metals are often catalysts for our enzyme systems. They're frequently involved in electron transport redox-type reactions for energy transfer. Metallic compounds also often oxidize, losing or gaining an electron or 2 or 3 as part of their function and their role in these compounds. Metals are generally chelated. Chelated means essentially that they're wrapped in a hydrocarbon chain, which enables their biologic function, activity, and interface. Organic chemistry nomenclature. The most basic structures in organic chemistry are carbon chains, typically with hydrogen together, known as hydrocarbons. The basic naming is done by the number of carbons in the chain. 3 carbons would be propane, with the last 3 letters designating the carbons as being joined by single bonds. The top drawing shows the hydrogens. The bottom drawing shows the bare carbon chain. Both types of structure are commonly used. Again, each carbon has about a 120-degree angle between the bonds, and if you look at this compound below, R is anything. It could be another hydrocarbon chain, it could be an element, it could be anything at all. But the important concept is to look at that central carbon, and you see there's essentially a straight line to the left for the R, there's a straight line going straight up for the H, but one H has got that dashed line reflecting that it's behind the carbon to some degree, and the other one has the triangular bond indicating that the hydrogen is actually sticking out of the screen towards us. So carbon chain types, if it's all single bonds, the compound will end with the letters ANE. If they have double bonds, it will end in ENE, and triple bonded carbons will be YNE. 2 carbons would be prefaced with an ETH, 3 with a PROP, 4 with a BUT, 5 PNT, 6 HEX, and so on. So a 3-carbon chain with just hydrocarbon with hydrogens around it and no double bonds would be propane. If there was one double bond in the middle of that, that would be propene, and if it was a triple bond, it would be propyne. Double bonds do not allow carbon rotation as a single bond. Well, the single bonded carbons can just rotate around in a 180-degree to 360-degree spin, but when there's a double bond, that spin is not possible. Also note, with a double bond, the hydrogens are missing, thus this carbon chain would be called unsaturated. Double bonds are denoted either as cis or trans. In cis, you'll see that the CH3 groups are both on the same side of the double bonded carbons, and the hydrogens are on the same side below. But in the trans configuration, one of the CH3s is on the top and the other one is on the bottom. This is essentially an asymmetric bond molecule and can form what we call an isomer. Trans fats are the bad fats. Our enzymes don't degrade them well. A chiral molecule has an asymmetric carbon atom with a non-superimposable mirror image. Carbohydrate sugars are D designated, amino acids are L designated, and what this means is that polarized light passing through a pure compound will be rotated a little bit to the right if it's a D or to the left if it's an L. And if you look at the diagram below, you'll get a better handle on exactly what that means. You'll notice that the R is toward the middle on both of them, the right hand and the left hand. There's a COOH on the top. There is a NH2 on the bottom, and hydrogens off to where the thumbs are located. So one of these compounds would rotate polarized light to the left, the other one would rotate it to the right. Functional groups. Alcohols have an OH group and they end in OL. Alkyl halides have a carbon bonded to a halide group, members such as chlorine or fluorine. Ketones have a carbon with a double bond to an oxygen. They end in ONE, such as acetone. Aldehydes have a carbon with a double bond to oxygen and a single bond to hydrogen, ending in AL as a term. Carboxylic acids have a carbon with a double bond to oxygen and an OH bond, which can donate a proton. They will be termed as an oic acid. Ethers are carbons with a central oxygen. Esters are sweet-smelling. They're similar to ethers, but there's a double bond on that oxygen, and they end with the letters OATE. Amines have an NH2 group bound to the carbon with a prefix of amino. Amides, on the other hand, have a carbon with a double bond to oxygen and then a single bond to the amine group, and the term that ends with the suffix amide, amide. Polar characteristics of organic chemistry are important. This is not polar as in the North Pole and get your parka. This is polar as in dipoles like a magnet and where the electrons tend to be concentrated. Hydrocarbon chains are what we call hydrophobic or water-hating. Oil does not mix well with water. Oil is a hydrocarbon chain. Ionic compounds, such as alcohols, carboxylic acids, charged groups with sulfates, phosphates, have an electric charge at one end of a carbon chain and a long hydrocarbon chain behind them. They can act as detergents. One end of that molecule will mix well with water, the end that has the polar charge to it. The other end of the hydrocarbon would not mix well with water. So in the diagram below, R could be a 30-carbon chain or whatever you want it to do. And in this case, it would react very poorly with water, but then when you put a phosphate group, now all of a sudden, look at all those oxygens you have at that end. Those oxygens are going to kind of suck the electron cloud of the molecule down to their end of the chain and put some charge there, which means it will react well with water, and it will be the hydrophilic or water-loving end of the carbon chain. And then the other end of that carbon chain, where there is no polar effect of excess electrons, would be known as the hydrophobic end, or the fatty end that does not want water. Try to visualize the electron cloud of this larger molecule. Okay, it would likely be composed of carbon, oxygen, phosphorus, hydrogen, and again, the oxygen, the phosphorus, sulfur, whatever else is there are going to be kind of sucking the electron cloud a little bit closer down to their end of the chain, leaving the other end of the chain a little bit deficient in an electron cloud. The electron density will interact well with water in a water-loving manner. The hydrocarbon chain will not want to interact with water, but would rather react with other hydrocarbon chains. This interaction in an aqueous water-based environment, the phosphate groups will face outward, and the hydrocarbons will form their own layer. We're going to get into more of that in the cell biology section, which will come after the chemistry section. Hydrophobic, anybody who's tried to separate a thin plastic baggie on a cold day will know that plastic wants to bind to itself. Even though there's no glue, the plastic carbons like to stick together, and that's part of the hydrophobic aspect. It doesn't like water, but it does like to stick to itself or others like it. This happens every day in our body. These long chains of atoms are made again of carbon, nitrogen, oxygen, phosphorus, hydrogen, sulfur, and other elements. As these long molecules are formed, they assume specific configurations. Amino acids and peptides and proteins are what we'll talk about next. This is the basic chemical structure of these guys. And you'll see at the one end, there's an amino group with an NH2. At the other end, there's a carboxylic acid group with a C double bond O and an OH. Now, if it's all by itself and not bound into a long repeating chain called a polymer, that amine group with the nitrogen, where there are some other paired electrons, will also have a bit of a participation in hydrogen bonding and ionic separation, so it will tend to like water and bond well with water. The same thing will happen at the C double bond OH end, but what will happen ultimately is these two guys can get together, linking end to end, and we'll go into that in a little bit. But amino acids are basically pretty simple compounds when you get to the basis of them, and you'll see there's a red R below that. There are 23 main amino acids, and the R is different in each one of them, but the basic two-carbon chain up there will be the same in all of them. There are the building blocks for peptides. Peptides are basically short chains of amino acids. They link the carboxylic acid group to the amino group of the next amino acid, producing the dipeptide plus a water molecule. So you can see in this diagram how the water was formed when these two guys got together. The primary structure of a peptide describes the constituents in a linear sequence as it's formed. A peptide is a term to describe a short chain of amino acids. A protein would be a much longer chain. Carbohydrates, such as glycogen, are repeating sequences of sugar molecules. There are a variety of different sugars that exist. They're all described based on their arrangement of atoms in the groups around the carbon chain in an isomer fashion. Again, isomer, think of the diagram earlier that had the two hands, and that gives you an idea of what those molecules will be like. Aminoglycans are peptides or protein amino acid chains with attached side chains of carbohydrates. They work well to absorb water and they lubricate surfaces. They're present in our joints, for instance. The secondary structure of these peptides and other molecules refers to the highly regular repetition of local substructures. These are defined by hydrogen bonds and ionic attractions. These bonds cause the folding of the chain that undergoes as it's being formed. The angles of the elements joining together also cause the chain of smaller units to fold on itself in a specific format. Silk is a sequence of beta-pleated sheets of a monomer or repeating unit that forms a polymer or a series of repeating units. Polyester is a repeating sequence of ester chains as described below, or as visualized below. The tertiary structure refers to the three-dimensional structure of a single, double, or triple bonded protein molecule. Alpha helixes and beta-pleated sheets can fold into a compact globular structure. This folding is typically driven by non-specific hydrophobic interactions. It's not so much something that water gets into, it's more the carbons and hydrogens pulling things together. This structure is stable only when parts of a protein domain are locked into space by specific tertiary interactions, such as salt bridges, hydrogen bonds, and disulfide bonds. As far as a salt bridge, remember what I said earlier, that a carboxylic acid will tend to lose that protein and gain a negative charge. The amine group at physiologic pH will tend to gain a proton and have a slight positive charge. The salt bridge refers to the fact that there's a positively charged and a negatively charged. They're not covalently bonded, but they do kind of tend to attract each other. Sulfur will do the same thing to another sulfur, and of course hydrogen bonds we've already reviewed. And this is an example of what these things would look like. Quaternary structure. This is a three-dimensional structure of a multi-subunit proton and how the subunits fit together. It's stabilized by non-covalent interactions, and typically disulfide bonds is a tertiary structure. Hemoglobin, for instance, has an alpha and beta chain that each contain iron in either the ferrous F2 normal state or occasionally the ferric F3 plus abnormal state known as methemoglobin. This is a state that cannot transfer oxygen. It's oxidized and needs to be reduced from ferric to ferrous in order to function. You can just barely make out the 4 iron atoms with the 2 green alpha chains and the 2 yellow beta chains. We'll review carbohydrates now. Carbohydrates are basically common biological sugars that generally have 5 or 6 carbon atoms and are more properly called sugar alcohols due to the R-OH of repeating structures. They can be straight chains or ring-shaped, and in the natural physiologic state they can very easily and quickly change from these two shapes. Glucose would be an example. Here you have a cyclic glucose, a circle of glucose, and it can also convert into a straight chain. For the sake of ease of drawing, straight chains are usually a little bit easier to visualize, but if you pay attention, you can look carefully at the cyclic form and have an understanding of how that works too. Looking at the straight chain, you'll see that there are hydroxys on the right, then the left, then 2 on the right. To change from glucose to a different molecule, a different sugar, you would just simply take the OH, the hydroxy group, and move one of them onto the other side where the H is. And these are asymmetric carbons because of the C double bond O and just the overall format of them. And the C double bond O up there, one side leads off to an H, the other side leads to the long complex hydrocarbon chain that for shorthand will be described with the letter R. Hexoses are 6 carbon sugars, and you can see that between glucose and mannose there's just some differences on where the OH is, and you have the linear form above and the cyclic form below. Pentose is a family of 5 carbon sugars that can also be in straight or ring form. Remember that all sugar carbohydrates are D isomers that rotate polarized light to the right. The L isomer sugars are not biologically active. With amino acids come in the L form, and any D form amino acids, again, would not be biologically active. Ribose is a typical pentose, or 5 carbon sugar. It's used as part of the nucleic acid base structures of our DNA, and this is what it would look like. Glycogen is a branched chain storage form of glucose that is primarily found in liver and muscles. It can be burned to produce energy without oxygen, but this process is quite inefficient. And this is what glycogen would look like, and you can see there's a couple of branches. There's, let's see, 1, 2, 3 branches available on this particular diagram. Sterols will be the next area that we're going to review. Sterol is the term for a basic structure. This is what it looks like in shorthand. And you can see that basically there are three 6-carbon rings and 1 5-carbon ring. And these are basically fats. This class would include cholesterol. And despite all the bad press, cholesterol is very important. It's got a bad rap. You can see the basic 4-ring structure, And then on the upper right-hand corner, there's a hydrocarbon chain. In the lower left-hand corner, there's a hydroxy chain sticking out. And this basically is the big difference between a sterol and cholesterol. Cholesterol forms the basis for sex hormone formation. DHEA, dihydroepiandrosterone, is the parent compound for the sex steroids, and this is what it looks like. And you can see it's got pretty much a typical sterol structure. In the upper right-hand corner, there's a double bond to oxygen that comes off the pentamer carbon. Testosterone is a little bit different. Instead of a double bond to oxygen, there's an OH there. And in the lower left-hand corner, where there was an OH, there's now a double bond to oxygen. Estrogen is a little bit different. It's got the OH in the bottom, and it's got the double bond O back at the top, similar to DHEA. So you could really almost say that it's just a couple of hydrogens, and where they're placed, there's a difference between men and women. Vive la différence, eh? And then progesterone is another sex steroid. And on the top of the 5-carbon chain, there's another carbon chain there with 2 carbons added to it. And in the lower left-hand corner, you see that there's the double O like there is with testosterone. So that's the basis of the sex hormones and what makes us men and women. Fatty acids are another set of building blocks for structural fats. And as we discussed earlier, if there's a double bond, and if you look at the bottom diagram, the 3rd and 4th carbon from the right, there's a double bond there. Where that double bond is, there could be room for 2 additional hydrogens, but they are not there. So this is an unsaturated or a monounsaturated structure that happens to be in the cis format. You can see the 2 hydrogens are both sticking up in the same direction. On the other hand, up at top, the hydrocarbon chain it's fully saturated. There is no room for any more hydrogens there. Fatty acids will have a phosphate group added at one end. So phosphatidylcholine is an essential component of a biological membrane. And this is what these look like. You can see the phosphate group and this one in the middle. It's a sphingomyelin, okay? And if you look below, you can see another compound where they've just sort of folded it over. It would have been a very long compound. It wouldn't have fit all in one piece of paper. So they just kind of folded it over in the middle where the action is, and you can see there's a phosphate group attached in there with an amine. Triglycerides consist of glycerol with attached fatty acids. So this is what glycerol looks like. It's basically a 3-carbon chain with 3 hydroxy groups on it. That's the OH group. And then in triglyceride, you've got long-chain fatty acids that tack into that OH group. And now you've got an unsaturated triglyceride, and it's unsaturated because you can see where there's some double bonds drawn in there. If it was a saturated triglyceride, there would be no double bonds. It would all be filled with hydrogens. There are some basic rules for structural components. A polymer is composed of repeating identical monomers, such as repeating glucose molecules, that can form starch if it's unbranched, or if it's branched, it will form glycogen. When monomers gather and link up to produce a polymer, generally water is produced. Conversely, a polymer can react with an acid, alkaline, or enzymatic reaction to break into its constituent monomers. Basic rules: continued long complex molecules of different compounds can also form so that amino acids form peptides and proteins, or glucosamines, in which amino acids join up to carbohydrate and then peptide chains. Again, a peptide is a short protein or chain of amino acids. Peptides can also link up with fats. Sugars, carbohydrates can link up with fats or peptides. All combinations are used and they all work well together. So again, a peptide can join to other peptides, lipids, which is a fat, sugars, carbohydrates, or a carbohydrate can join to carbohydrates, lipids, or peptides. Lipids can join to lipid, carbohydrate, or peptide. And also other moieties can link in, including metals, phosphate groups, etc. I hope you've found this beneficial, this review of general and organic chemistry, We're going to take these concepts next and relate to molecular biology and how our basic cells function. And from there, we'll move further through the vitamins, minerals, supplements, and everything else to better understand how they work in our bodies. Thank you for paying attention.